Now, in the case of compounds in which one atom has 3 electron domains, let's say, for example, ethylene, which is shown to have this formula. Okay, ethylene has this Lewis structure. Okay, that carbon is bonded to hydrogens, and you have a double bond there, carbon, another hydrogen, another hydrogen. Each of these carbons have trigonal planar geometries. Okay, trigonal planar geometries. And notice that they have 3 electron domains each, basically 2 single bonds, okay, and 1 double bond. So according to hybridization, there are actually 3 electrons from each carbon which are involved in sigma bonding, and they are in this thing called the sp2 hybrid orbitals. Okay, so sp2, there are only 3 electrons involved. Now, how did we come up with this orbital arrangement? Again, similar assumptions that we have done for sp3 hybrid orbitals also happen, except also take into account, except that for this case, this involves just the hybridization of one s orbital and 2 p orbitals. So there's actually 3 sp2 hybrid orbitals. Okay, that actually leaves one 2p orbital of carbon unhybridized. Okay, so again, sp2 hybrid orbitals are for molecules or atoms of molecules with a trigonal planar molecular geometry. Okay, now if you have, for example, boron trifluoride, so boron in boron trifluoride is also sp2 hybridized. Okay, so boron trifluoride has trigonal planar Lewis structure. Now that not that 2p orbital around boron trifluoride is actually empty. Okay, so here we can say for boron trifluoride you have two sp2 orbitals have failed. Okay, and those are the ones which bonded fluorine 2p orbitals. Okay, 2sp have failed. Okay, and then one p unhybridized, one 2p rather unhybridized orbital. Let's just put there 2 unhybridized orbital unfilled. Okay. Now notice that the 2p orbital is higher in energy than the sp2 orbitals, but we're not going to go into that detail, at least for the scope of this class. Now, as we have mentioned, those sp3 orbitals from ethane can actually overlap head-on to form sigma bonds. So for ethylene, you have 3 sp2 hybrid orbitals for each carbon. 2 of those sp2 hybrid orbitals for each carbon will bond with the 1s orbital of hydrogen. Okay, so that actually leaves just one sp2 hybridized orbital still available for bonding. And that sp2 hybrid orbital also forms yet another sigma bond with another sp2 hybrid orbital, this time from the other carbon. Okay, now those unhybridized p orbitals are still there. Okay, however, they do not overlap head-on. Instead, they actually overlap sideways like this. Okay, now the sideways overlap is a different kind of bond. It's actually a pi bond instead. The pi bond is a sideways overlap, okay, of unhybridized p orbitals. And again, the takeaway message here is it is not a head-on overlap. So every time you see a double bond, so just think of it as one of those bonds in the double bond is a sigma bond, and the other one should be as a result of a pi bond from an hybridized p orbitals. Okay, now if we go to an organic molecule with a triple bond such as acetylene. So acetylene has a linear structure. Each carbon again has a linear configuration, or this molecule has a linear configuration. This carbon and that other carbon have each 2 electron domains. Okay, so 2 electron domains. Now, if you have 2 electron domains, and if you have 2 electron domains, all of them are bonding, then according to hybridization rules, you should have an sp hybridized atom. Okay, so for this one, note that this is actually the combination of one 2s orbital and one 2p orbital, at least for carbon. Okay, and that actually leaves you with 2 unhybridized 2p orbitals. These 2 electrons will be available for sigma bonding. Okay, and like what we have seen before, one of those 2 sp orbitals will be available for sigma bonding with 1h of hydrogen, or sorry, 1s of hydrogen, and the other one will be involved with sigma bonding of yet another sp hybrid orbital from the other hydrogen, or the other carbon rather. Now, as you can see, those 2 unhybridized p orbitals, this one and basically this one, they're perpendicular to each other, okay? But when carbon bonds with carbon, those p orbitals actually overlap sideways to form pi bonds. So, for example, so for acetylene, to simplify that, if you see a carbon with 2 electron domains and it has this structure, okay? So basically, you can identify this as a sigma bond, okay? Now, this is a sigma bond as well. Oops, wrong sign, but there you go. And then this, one of these triple bonds is a pi bond, and the other one should be a pi bond as well. Okay, now if you have, again, sp hybrid orbitals apply for 2 electron domains. So let's say, for example, if you have CO2, okay, if you have carbon dioxide, then one of these should be sigma, the other one should be sigma, and then this one should be pi, then this should be pi, okay? Now, and that's actually what I just explained earlier. I guess I just got ahead of myself. So, now, if you have, for example, atoms which violate the octet rule, such as phosphorus and phosphorus pentafluoride, or sulfur and sulfur hexafluoride, so pretty much we are now at the 3s and 3p orbitals in terms of valence shell. Okay. Sure, according to this one, we also have empty 4s orbitals. Let's for now just consider the 3d orbitals because they have the same principal quantum number as 3s and 3p. So doing the same thought experiment that we did before, if we promote one of the 3s electrons into the empty 3d orbital, then we will have this scenario. And again, this is for phosphorus pentachloride. Note, however, that there's only 3 electrons there, which will make 3 equivalent bonds. Okay, those are the ones from 3p. So basically here, you're going to have 3 kinds of electron bonds, or of bonds. And there are 3 only which are equivalent to each other. So what we're going to do is we're actually going to hybridize these orbitals together. Okay, and in doing so, now we have a dsp3 hybrid orbital, or in some textbooks they actually call it sp3d. Okay, I'm just sticking with dsp3 because that's what your book actually wants to stick with. Okay, so a dsp3 orbital again is for geometries with 5 electron domains. Okay, it doesn't matter whether they're bonding or non-bonding. Okay, so 5 electron domains, and since we have 5 electron domains, the electron pair configuration or electron pair geometry for this one should be trigonal bipyramidal. So that's what the shape of a dsp3 hybrid orbital looks like. And note that as a result of the hybridization, we have 4 empty 3D orbitals. Okay. And then now if we have 6 electron domains, okay, again, doesn't matter whether it's bonding or non-bonding, then we have an octahedral electron pair geometry. Now for D2sp3, which is for 6 electron domains, this involves the hybridization of 2 3D orbitals, 1 3s orbital, and then 3 3p orbitals, at least for sulfur here. So this also leaves behind 3 3D empty orbitals. Okay, so just a quick review. So what we have is, so far we have four electron domains, sp3. Okay, the sum of s and p, the exponents are 1 plus 3, 4. We also have trigonal planar, sp2. We also have linear sp. We have next trigonal bipyramidal, which is dsp3. Okay, that's an electron, or that's electron domains equal to 5. And then 6 electron domains will be d2sp3, and that's octahedral. Okay, let's just answer this exercise, and then we will answer the other exercises in class online. Okay, so we want to know the hybridization of carbon, nitrogen, and oxygen. Okay, so let's start first with 1 nitrogen, because if we actually answer 1 nitrogen, then we've answered all of them already. Okay, so for the hybridization here of nitrogen, so you can see this has 1 electron domain, 2 electron domains, 3 electron domains, and there's actually 4 electron domains around nitrogen. It just so happens that one of them is a lone pair, and 3 of them are bonding pairs. So therefore, nitrogen here, as well as this other nitrogen, should be sp3 hybridized. Okay, and then next, this carbon has 1, 2, 3 electron domains. So the carbon should be sp2 hybridized. And for this oxygen, it has 1, 2, 3 electron domains. So this one should also be sp2 hybridized.